Hello, physics students. Here is the answers to the test, Unit 2, Part 1, the vector test. Okay, this is problem number 1. Okay, and please just pay attention. If you can go ahead and fast forward this video if you were pretty confident in number 1 and you wanted to look at number 2. This video is going to go through each of the problems. So yeah, if you want to fast forward or slow down or stop or rewind, by all means do so. Okay, first and foremost, I'm setting up two different scenarios here. The first scenario, okay, being for part A of problem 1, and that would be this top line here. We'd have a terminal and we have a departure gate. Okay, and in the problem, it states that the moving sidewalk is moving at a velocity of 0.90 meters per second towards the departure gate. Okay, so we know that the moving sidewalk has a velocity. Okay, and we're going to call this side positive and this side negative. Okay, and the velocity is going to be 0.90 meters per second. Now, you'll notice that's positive because the velocity is towards the departure gate. Now, there's also a man on this particular moving sidewalk. So we're going to go ahead and just draw a guy here. All right, and he is moving with a velocity of 1 meter per second, also in the direction of the departure gate. So that also will be positive. Now the question is, what is the relative velocity to the ground? Well, the moving sidewalk is moving the man at 0.9 meters per second. He is moving himself at an additional 1 meter per second. So the total velocity of the man relative to the ground is going to be the addition of these two values. So the velocity of the man relative to the ground, so we're going to go velocity man to ground, is going to be the addition of the two, 1 meter per second plus 0.90 meters per second, which is really just going to be 1.9 meters per second. Okay, so that was the first part. That was part A. Okay, part B, okay, was a little different. Okay, it was a similar sidewalk, but moving in the opposite direction. Okay, so this particular sidewalk had a velocity of 0.90 meters per second, but, okay, this is still positive. This is still negative. This is still the departure gate. This is the terminal. But because the sidewalk is moving towards the terminal, its velocity is similar, very important wording in the problem, but not the same. So it's going to be 0.90 meters per second, but in the negative direction. Now the child on the moving sidewalk is also moving towards the terminal. Okay, so that child, and we'll go ahead and draw that child here. A smaller being. The child has a velocity also, but it's in the negative direction. So the child's velocity, and I'll draw it on the other side of the child just to kind of emphasize the opposite direction, is going to be a negative 0.4 meters per second. Okay, so the total velocity of to an observer on the ground of the child on the moving sidewalk is going to be the addition of these two vectors. Okay, so the velocity of the child to ground is going to equal a negative 1.3 meters per second. But in problem B, that's not what they were asking. In problem B, what they were asking is how fast is the man moving relative to the child? Okay, so to go ahead and analyze that, now that we have these two vectors relative to the ground, we can go ahead and look at on this side. Okay, and I'm going to go ahead. You'll notice that the man is blue, the child is red. Okay, well, the man was blue, and his velocity was 1.9 meters per second in the positive direction. And the child was moving in a negative direction. Okay, so we're going to put that over here at a negative 1.3 meters per second. Now, we know from working with vector diagrams that we cannot add these two unless they are tail to tip. And in order to make them tail to tip, I would have to subtract one from the other. Now, because we're going, you'll notice that they're both kind of connected here because this is the perspective from the ground. Okay, so if we want to get an idea of what the man's velocity was, we're going to go ahead and subtract what the red vector, or the one on the left. Okay, so to subtract that mathematically, we would do something like this. Okay, we would take the man's vector, 1.9 meters per second, and we're going to go ahead and subtract, okay, the child's velocity in the opposite direction, so a negative 1.3 meters per second. Okay, and what this ends up being then is 1.9 meters per second minus a negative, so this will become positive, gives me 3.2 meters per second in the positive direction. Now the question we have to ask ourselves is, does this make sense? Okay, and if we wanted to rationalize this, we could. First of all, the child and the man are moving away from each other. Just like when two cars are moving away from each other, they look like they're traveling faster than they really are. Okay, so they obviously, the man is going to appear to be moving faster to the child than he really is. This answer fits that. Also, the answer is positive, and the answer should be positive because it's what in which direction is the man traveling relative to the child. Okay, and the man is traveling in the positive direction, has always been traveling in the positive direction. Therefore, the answer should be positive. So this answer does make sense. It fits all of the criteria. It rationally it makes sense, logically it makes sense, and mathematically it makes sense. So this was the answer to problem number 1. Now, problem number 2. Okay, this particular problem seemed to cause a lot of grief for people, and I just want to specify that this will be one of the easier problems of this unit. Not easy by any means, but easier. And so if you're really struggling with vectors and component vectors, please come see me. First of all, you were supposed to diagram the motion of the helicopter, and this is what it should have looked like, labeling this vector A, this vector B, and this vector C. Okay, now I am going to analyze this purely from an A, B, C standpoint, looking at A individually, B individually, and C individually. And actually, the way that the problem was worded, there's two ways you could analyze C that'll give two reasonable answers. Okay, so nonetheless, please be aware of the fact that this is the way that you should have analyzed this particular motion of the helicopter, this particular problem. Okay, first and foremost, I'm going to go ahead and write times on here because each part of the trip was given a unique time. Okay, so the time for A was 11 seconds. The time for B was 0.250 seconds. And the time for C was 6 seconds. Okay, now with that information, okay, we can go ahead and compile distances. It was stated in the beginning of the problem that the helicopter's velocity was constant. Or I should probably say speed. The helicopter's speed is constant. Okay, so the helicopter's speed is 4 meters per second. Okay, well, if you travel at 4 meters per second for 11 seconds, you're traveling 44 meters. And if you travel at 0.25 seconds, you're really going to travel a distance of 1.0 meter. And at C, if you're traveling at a velocity of 4 meters per second for 6 seconds, okay, you're going to go ahead and I'm going to go ahead and move these out of the way a little bit. Okay, and if it's C, you're going to go ahead and travel a total distance of 24 meters. So for part B, when it asks for total distance, you just add up the distance traveled over each component or each distance ABC. Okay, so it's going to be a total of 44.0 meters plus 1.0 meters plus 24.0 meters, which is a grand total of 69.0 meters. You might be wondering why I haven't incorporated any negative values, and we will in just a moment. When we're dealing with total distance, you cannot travel a negative distance. You can have a negative displacement, but that's not what was asked in the problem. Distance is always positive. Okay, so in this particular problem, because we were looking at a total distance, okay, we could add each of the distances of each of the vectors, and it gives us a total distance traveled of 69 meters. I could have taken this a step further by going ahead and asking you what the average speed of the helicopter was for its trip, but unfortunately, because of the way it was worded, there was a couple of moments where where the helicopter plummets and then recovers, where we wouldn't have necessarily had a full picture of how long the helicopter was in the air. So I didn't ask that question, but I could have, and you'll see something similar to that kind of question on the next test. Okay, so this was total distance. Here were the values, okay? And for part C, I asked you to write the equations for the component vectors, the horizontal and vertical components. The equations I were looking for were r cosine theta equals rx and r sine theta equals ry. Two generic expressions, one for the horizontal, here, motion, and one for the vertical, this motion here. The reason this is horizontal is that cosine also deals with x. X is this direction, left to right. Y, also corresponding to the sine, deals with the motion up and down. Okay, so these are the two equations I was looking for. Okay, you could have used A instead of R. You could have just put A cosine theta or B cosine theta or A sine theta, B sine theta, etc. But this is what I wanted to see. I didn't want to see numbers because it asked for equations. Okay, two equations should be written here is what it said. All right, so now using these equations and these values and the information given in the problem, we can go ahead and analyze the different component vectors of each of the vectors. And this is where it gets tricky. Okay, so what I'm going to go ahead and do is I'm going to go ahead and I'm going to want some of this information. So I'm going to go ahead and copy a bunch of information, and I'm going to put it on the next slide and delete some things. Okay, first and foremost, I'm going to go ahead and delete, okay, the times. We're not going to necessarily need those anymore. We have distances, which are important. Okay, and we can leave that. I'm going to also delete, okay, this total distance business, okay, because we're not going to use that anymore either. Okay, I can delete these arrows, and I'm going to delete that there. Okay, so I'm going to move some of this information around. Okay, we're going to use this equation, and we're going to use this equation, so I'm just going to kind of put them off to the side. And we need to add a few things that I haven't yet included in my diagram. First and foremost, we can go ahead and make this 63 degrees. Now, the tricky part to this was that there was two ways to analyze vector C, okay? I'm going to go ahead and draw some red arrows here. You could have analyzed vector C from this angle, being 15 degrees, and that would have been the best choice, okay? Some people I know chose to analyze this from this angle being 15 degrees. Okay, it does actually make a difference. Okay, if you analyzed it from this lower angle, 15 degrees, the one I'm circling, if you're it's green, okay, then that means that you actually dropped 75 degrees more towards the ground than you would have if you'd analyzed it in this way. The way it was worded in the problem, you could have taken it either way. Okay, so what I'm going to go ahead and do is I'm going to work everything in terms of the 15 degrees that I am circling here, okay, the one below this upper horizontal, and I will just add the values in green if you had done it this way. Okay, the process is relatively the same, but the values are a little different. Okay, so if you have any questions about that, you can come see me, but please be aware you could have analyzed this in two ways to get it correct, which does give you two very different answers. Okay, so for part D, parts uh, 1, 2, and 3, we're going to look at AX, AY, BX, BY, CX, CY. Okay, so I'm going to go ahead and just write those in right now. Okay, if you did the calculations correctly, here are the values you could have expected to see. For AX, you should have gotten something about 19.976. What this value is it's AX refers to the A vector in the X direction. So it would be, go ahead and be this part of, it would be like that distance right there. Okay. For BX, you should have gotten 0 meters because vector B does not move in the X direction left to right at all. So there is no motion in the X direction. And in CX, okay, you could have gotten 23.18 meters. Okay, now if this was 15 degrees, we would expect X to be much longer than Y, being that this is such a small angle. So we're going to expect this CX to be larger than CY. If you did it the other way, we would expect the opposite. Okay, so that distance there should be this distance here. Okay, now for our Y, okay, um, and I guess I'll go ahead and add in right now the CX for the alternate method should have been a 6.212. All right, AY should have technically have been 39.204. Remember, I use more decimals when I'm actually working my problem, and I round at the end. Okay, just to kind of keep things as accurate as possible. But my final answer should reflect a proper measurement, which means that it should reflect proper significant figures. Okay, so that would be this. And this distance here, 39.204 for AY, would be this full distance here. Okay, now, if I go ahead and analyze BY, I had to define a coordinate system. Okay, this is positive in the up direction. So any motion in the opposite up or any motion down is going to be negative. So BY was a distance of 1 meter, but it should have been a negative 1.0 meters when it came to the component vector. And CY also was in the down direction. Regardless of how you did the problem, CY was going to be negative. So it's going to be a negative 6.212 meters. If you did the alternative method, here in the green, it would have been a negative 23.18. So you'll just notice that it's really if you did the alternative method, these two values here, cx and cy, just switched, but the cy maintains the negative value because it is still in the negative direction. Okay, and what we see happening is that we move in a downward direction. So we go in this direction, and then we add cy, which is in this direction. Now, please note, my vector does not go back down to the ground. I do not know if the helicopter landed. It is not implied in the problem. So we have to assume that the helicopter did not touch the ground. It could have, but we won't know that until we're finally done with the problem. Okay, so please be aware of that. Okay, so just a couple of things there. I'm going to go ahead and delete some of these things so that they're not clogging up the screen. Okay, we'll leave it right there for a moment. So here's our different values: AX, BX, CX, CX alternative, AY, BY, CY, CY alternative. Okay, and I'm going to go ahead and copy these to the next slide. At this point, we're pretty much done with the diagram. Okay, now it's purely a mathematical approach. So we're going to go ahead and look at the math. And it should be, there it is. Okay, what we want to do is we want to calculate Rx and Ry, our resultant components. So we're going to go ahead and calculate Rx, excuse me, and Ry. Rx is just the addition of these values here, 19.976 meters, and Cx to 23.18 meters. Rx ends up being 43.156. Okay, our y is just the addition of all of these, but because there are negative displacements here, it's going to take away from our initial displacement of 39.204. So even though we're adding these, there's going to be some subtraction. Okay, and our final ry component is going to be 31.992 meters. Okay, I'm going to go ahead and just draw a line to kind of separate these values, just so that we have a better idea here. And we're going to go ahead and show the alternative calculation. If you used the 15 degrees in the previous problem as indicated by the green here, then your Rx and Ry would have been different, okay, and significantly different. So Rx would have ended up working out to be 26.188 meters, and Ry would have been something like 15.024 meters. Okay, so here's kind of what you could have expected to see. All right, now these values, that ends part D of this particular problem. What we're going to do now when we move on to E and F is we're going to copy, okay, these values to the next slide and use them in yet further calculations. Okay, once we know Rx and Ry, we're going to go ahead and use them to find the resultant. This is where the equation, Pythagorean theorem, comes into play. Okay, we know that the Pythagorean theorem for the resultant is R equals the square root of Rx squared plus Ry squared. Okay, the same is going to be true for the green value. So it's not like we have one Pythagorean theorem for our first one and second one. We're using the same equation. Okay, so our R value, once the numbers are plugged in, the math should be relatively straightforward. The R value would have been about 53.72. Okay, because the problem only gives our work to two significant figures, the answer really should be 54 meters. That should be our resultant. Okay, now I'm going to get into angles in just a minute. Now, for the green answer would have been, okay, R is roughly equal to 30 meters. Okay, so these are the two answers you should have expected to see. Now, these do make sense. 54 meters is greater than Rx and Ry as the resultant should be. And 30 meters is greater than 26 and greater than 15.024. So that also makes sense. So these values do indeed make sense for our calculations. Okay, so we're going to go ahead and now calculate the angles. Okay, for the first or the black method here that I'm doing for the 54 meters, the angle should have been, and I always use inverse tangent, of Rx, or excuse me, Ry over Rx, opposite over adjacent. Okay, so in this particular case, the angle would have been 37 degrees. Roughly. It would have come out to like 36 and a half, but to two significant figures, the degree is 37. So our final answer for this would have been 54 meters at 37 degrees above the horizontal. Okay. Now, our the green alternative method, same thing, Ry and Rx. You're just using a different Ry and a different Rx, and you end up with an angle that is very much different. It's going to be 30 degrees. Okay, so the angle ends up being something like 30 degrees, which is not as great an angle. And I'll show you why that makes sense here in just a minute. So our answer would have been 30 meters at 30 degrees above the horizontal. All right, if we go back a few slides here to our diagram right here, if this was the 15-degree angle, we would have expected this line to be much steeper, maybe something like this. Okay, and if that was the case, the displacement wouldn't have been nearly as far, and the angle wouldn't have been nearly as much. Okay, so for our alternative method, that makes sense. The displacement is less, and the angle is less. Whereas if we had to use the 15 degrees that I would have intuitively used for this problem, this one up here, okay, we would have seen that there would have been more of a travel in the x direction. Hence, this vector would have been higher off the ground, giving us a greater angle, and more distance would have been achieved from our initial starting position, so the displacement would have been greater. And that is also what we see in the answer. So both of these answers are legitimate answers. Okay, R is roughly equal to 54 meters at 37 degrees above the horizontal, or R could have been equal to 30 meters at 30 degrees above the horizontal. Both of these answers are excellent answers, and if you got them, congratulations. If you made some minor mistakes along the way, I hope that this video helped clarify those. Please, please, please come see me if you have any questions concerning these. I mean, I obviously went through this in much detail. As you can see, I went through all of this test. But if you have questions, you don't quite understand one of the things that I did, I think it'd be very helpful for you to come see me and maybe work another practice problem. So anyway, I hope that this helped, and this is the end of the recording. Have a great night.